Hi and welcome back. So in the last video we were working on figuring out electron configurations for elements that occurred in our D block on the periodic table. And in this video I'm going to do a couple more examples, and I'm actually going to point out the couple exceptions that we have in the D block. So pretty much what we're trying to do is we're trying to set up rules for figuring out the electron configurations just based on where elements show up on the periodic table. And there are a couple of elements in our D block here that don't follow the rules that we're going to lay out. I think there are only two. And I'll try to make an addendum video if I find out that there are more than two, but there are, at least right now, there are two that I know about. And probably what we'll talk about, probably we won't get to it in this video, probably in the next video, is we'll start talking about this whole block down here, which I don't know if you remember at the beginning of the playlist, I think I called this the F block. The F block. So we are going to start talking about this, and what we're going to realize is that this F block is full of these exceptions, that we can try to sort of set up a rule, but lots of these elements that are down here in this F block don't necessarily completely adhere to the rule of where the electrons go in the orbitals. And maybe I'll do a video in the future to try to give you a little bit of an intuition about why that is. Probably I'll do that towards the end of the playlist. Whenever I get to it. But for right now, we're actually going to do a few more examples of doing electron configurations from this D block. So I'm going to clear off all my drawing. I'm just going to real quick write in the periods again. 1, 2, 3, 4, 5, 6, 7. And in this example, let's do the electron configuration for silver. And this isn't going to be one of our exceptions. So this is just going to be follow, I guess, the rules that we've set up. So if you want to try, hopefully you feel confident enough to try to figure out the electron configuration on your own. And I'd recommend that if you do feel that way, and even if you don't, I'd still recommend that you pause the video now and try to figure it out, and then unpause it, and I'll start writing it down. So hopefully you've unpaused the video now, and I'm going to start writing down the configuration for silver. So we're starting out with our 1s. We're following the Aufbau principle of filling up the electrons, the lowest energy orbitals first. So we're going to start out with 1s2. It's totally full. 2s2, 2p6, 3s2, 3p6, and then, so we are at this point right here. We've got a configuration. We've got an electron configuration that looks a lot like argon at this point. So now we move on to 4s2, 4s2, and now what do we do here? Well, we start backfilling, right? We start backfilling the next orbital. So we start backfilling our d orbitals. So our next orbital is going to be 3d10. So that gets us, we now have an electron configuration that looks like zinc. So this would be the electron configuration of zinc. So we have to keep going. We have to go all the way through this fourth period of our p block. So we're going to say 4p. And that p orbital is totally full, so we have 6 electrons in our p block. Now we move on to the 5th period, and silver is going to be in the 5th period. So we know that this is the last period that we're going to be filling up. So now we have got 5, and let me actually switch back colors. We're going to have 5s2, that s orbital is totally full. And now we're in our d block, and we're going to count over, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. So we know that silver is in this column that we have a 9 over. And so that means that we need 9 electrons inside of this d orbital. And which orbital is it going to be? Is it going to be the 5d orbital? Well, no, it's going to be this period that we're in minus 1. So our last entry in this table is going to be 4d9. And that should be our electron configuration. Just to check it, let's go through and add up all of our electrons. So we've got 2 plus 2 plus 6 is 10, plus 2 plus 2 plus 6 is 20, plus 10 gives us 30. Then we have 36, 38. So now we have 38 plus 9 should give us 47 electrons. And that's what we want. We want 47 electrons because we're looking at the neutral atom of silver. So this is our electron configuration of silver. So hopefully now you feel confident enough, and you could say that you feel confident enough to do the electron configurations from everything on the periodic table above this line that I just drew. Hopefully you feel confident enough for doing all of these different electron configurations. There are, now what I want to talk about, and I kind of, I guess, foreshadowed this at the beginning of this video, is that in this D block, and essentially above this line we've got a whole bunch of different elements, and you could say, because our last element is 54, so there are 54 elements that are above this line that we drew, and there are only two exceptions that don't really follow this rule. And those two exceptions, and this is, you might want to memorize this. This might not be necessarily the time exactly in the course where you're working on electron configurations, but it might be a good thing to keep in the back of your head. The two exceptions that are essentially above this line are going to be chromium and copper. Those are the two exceptions that don't necessarily completely follow this rule. So actually, I'm going to clear off all my drawing, and let's just draw in our periods again. 1, 2, 3, 4, 5, and I think that's all we need. Let's do the electron configuration for chromium, and let's figure out what we would essentially expect this electron configuration to look like. Well, we're going to start off using the Aufbau principle, so we're filling the lowest energy orbitals first. So we start off 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we start backfilling our 3d orbital. We've got 1, 2, 3, 4. So our 3d orbital, we would expect, and this is not the electron configuration for chromium. This is what we would expect it to be based on our rule, would be 3d4. That's essentially what we would expect. And this is almost right. The only part that isn't right is this last entry. That this is, according to our rule, this is what we would expect. But actually what we get is we get all of this stuff. So all of this, what's before, up to 3p6, all of that's right. But what happens here in chromium is we actually have 4s1, 3d5. And I'll talk more in detail about why this is. I'll give you just a brief explanation, maybe. And if you remember our d orbitals, so our d orbitals, we've got 5 of them. And if you heard, I don't know if I didn't mention it, or I definitely didn't dwell on it when I mentioned it earlier. But essentially, the way that we fill these orbitals is we fill these orbitals. Each orbital gets 1 electron first. So we fill in all the orbitals get 1 electron, and then after they each have their first electron, then they each get their second. So if we had an element an element with 3 electrons in the d orbital, say that our last entry was some number d3, that would look like this. So we would have essentially 1 electron in this d orbital, 1 electron in this d orbital, 1 electron in this d orbital. It wouldn't look like this. Okay? So hopefully you can see the difference where we would start out with 2 electrons in this first d orbital and then only 1 in the next. It wouldn't look like that. What we would do is we would put 1 electron into each orbital until every orbital has 1 electron. So this is essentially what this looks like right now is if we had some number d5. That's what this configuration would look like because we've got 1 electron in each d orbital. Now essentially what happens and I'll talk more about this in the future about why this is, and I don't think you necessarily need to know this now or need to understand it a ton right now, but essentially what happens with chromium is because we've got our 4s shell and we've got this 3d shell, and essentially what happens is there's a certain amount of stability associated with having a half-filled d shell. So it's almost, you could say, if you remember earlier on in the playlist, I talked about potential energy, and essentially, what we're going to be talking about when we say that an atom wants to do something, or that there's a strong tendency for an atom to do something, is that an atom essentially wants to get rid of its potential energy. It wants to, I guess, go to its lowest energy state. You can kind of think about, like, if I take a rubber band and I wind a rubber band up, or I stretch a rubber band out really, really long, that rubber band wants to go back to, if I have a rubber band and I stretch it out like that, that rubber band wants to go back to its equilibrium state, which maybe it's, I don't know, maybe it's something like that. Maybe that rubber band's only this big, so I've stretched it out like, maybe 3 times as long as it should be stretched out. That rubber band wants to go back to that equilibrium state. And essentially, what happens on the atomic level is if we look at these orbitals, and this is going to be difficult to erase, but essentially there's more stability. There's more stability. No, I didn't mean to do that. Or there's less stability in having something that looks like this, where we've got 2 electrons in. So essentially, we would have an electron configuration of this, because this would be. Anyway, I'm getting a little bit too ahead of myself. There's less stability in having this d orbital almost completely full than there is in having, or almost half full, than there is in having our 4s orbital half full. So if we had, I'll erase this electron down here. So if we had our 4s orbital half full, so we only have 1 electron down here, and then we would have our 3d orbital also half full. There's more stability in that configuration. Hopefully I didn't confuse you with that explanation. Really, if you don't understand it, don't worry about that. We'll definitely talk about this more in a future video. Actually, you know what? I think I'm going to end this video right now. In the next video, so essentially this is going to be our electronic configuration for chromium. It's going to be up to that point, so up to 3p6, and then the next entry is going to be 4s1, 3d5. In the next video, I'm going to talk about the other exception to the rules that we've set out for electron configuration, which is going to be copper. Anyway, thanks so much for watching, and I'll see you in the next video.